Hi, everyone. Thanks for joining us. We're going to wait about 2 more minutes for a few more people to join, and then we'll get started. So, thanks so much.
All right, Jess, you think we're good to get started?
Yeah, I think we're good to go.
All right, I will take it from here. So, hello, everyone. I see a lot of familiar names. Good to have you back. Today, we are going to be talking about different digester technologies. So, at a high level, for those of you that know Fluence, we're kind of split between municipal and industrial operations. My name is Jason Bowman, and I manage the North American operations for industrial wastewater and biogas. So what I like to focus on today, we'll give you 1 or 2 minute overview of Fluence in general, and then we'll talk about our approach to the digester market, why we have multiple technologies and the strategies behind those, as well as talk about actual applications, how these are applied, what process flow diagram might look like, what the operations look like, just to give everyone a general overview. So with that said, we'll get started. So Fluence at a high level, we are a multinational design, engineering, and technology firm. In the industrial wastewater and biogas space, we tend to focus more on a solutions mindset. So while we do have a large product portfolio, we have a lot of engineers with a lot of different experience. So we approach these projects more on a holistic or solutions approach. So in a lot of ways, it's more of a, let's say, European mentality where we do the design and evaluation up front and paint a roadmap for digester projects specifically. So one of the things I want to focus on today is kind of putting to rest some stereotypes on the larger digester market and focus more on, let's say, the industrial side, the small, the medium size. Not all digester projects are these mega digester projects, so that's something I want to talk about today. At a high level, you all may know Fluence. We're really split into kind of six focal areas. So we do a lot of decentralized treatment, desalination, wastewater treatment, water treatment, reuse, and then today we're going to focus specifically on the waste to energy. Within each of these six categories, Fluence is split in the municipal spectrum and split in the industrial spectrum. So We do have some products overlap between municipal and industrial, but there's also products specific for the industrial wastewater group and the biogas group that the municipal group does not have. So I want to start with this photo here, and this came out of the Biocycle magazine. So, in my travels and my experience meeting with end users, meeting with engineers, meeting with consultants, meeting with agents, developers, etc., there's kind of this common mentality that all these digester projects are just massive, right? You end up with these mega, multi 1 million, 2 million gallon tanks, and that is the only way that these digester projects make sense. So what I want to focus on today is the opposite of that, because that is not true. What Fluence has done a great job in is developing digesters for smaller, medium, more economical, more holistic industrial uses, rather than these large developer-driven or post-consumer manure type projects. So what I want to show here is the difference between what you see here on this slide and the next slide. So not all digester projects are these mega multi-million gallon digester facilities. So in fact, our bread and butter is more on the small and medium size digester projects, where we're looking at where the drivers are more like operational savings or pre-treatment, if you will. So again, we're going to flip back and forth here just so everyone kind of has a perspective. This is what most people think of when they think digesters. This is what we're talking about today, more of the smaller, holistic, decentralized digester styles that are geared more toward industrial independence and industrial operations. So as far as digester utilization, there's really three main categories on a global basis. When you think about commercialization and why these technologies are applied. So number one, digesters are used specifically for biogas operations. Developers use biogas facilities with the sole purpose of producing as much RNG or CNG as possible. So we're not going to focus on these projects today because they tend to be the larger side. There's economies of scale there. These are more applied to like manure, post-consumer landfill projects, energy crops, if you will. So what we're going to focus on today is how do we make this economical? How do we make this possible for private industries, for smaller and mid-sized industries? So we're going to focus on operational savings and pre-treatment as the drivers for digester technology. So within each of these categories, what we find is there are certain verticals, certain food and beverage manufacturing, certain industrial operations that fit one category or the other. Some fit within both categories, operational savings and pre-treatment. But more often than not, when we talk about dairies, confectionaries, prepared meals, big distilleries, breweries, and meat processing, digesters are typically applied for operational savings, right? These facilities have very high energy costs. It's difficult to put in an aerobic system just from an energy perspective and sludge perspective. Most of these facilities are going to operate with dissolved air flotation, so there's going to be a lot of solid product, primary sludge that comes out of these processes. So how do we minimize the headaches behind that? And we're going to talk about that today and how our digester technologies are applied in those areas. Then we have the pre-treatment side. So in most situations, industry, small and medium, typically go to a POTW discharge. Some facilities will go to the surface water, but more often than not, we're talking about going to a municipal situation where the effluent is being discharged directly to a municipality. So also very common in dairy, breweries, distillery processes, confectionaries, fruit juices, et cetera, et cetera. So we're going to talk about how we've developed technologies to focus on both these areas, the operational side and then the pre-treatment side. So before we do that, let's kind of take a step back to a 30,000-foot overview of anaerobic digestion in general and why why it's important for industrial operations. Well, number one, it helps to create industrial independence. So this can be independence from surcharges. This can be independence from energy. This can be independence from gas. There's a number of different ways that how we mean industrial independence. So why and how else are these digesters applied? Well, we just said pretreatment. So a lot of times we'll take the primary effluent from an industrial operation, we'll treat it to a specific standard, and we'll discharge it. In other situations, we'll treat it to a specific standard and we'll actually reuse it. We're not going to talk about that much today, but there is an option for that for those who are interested. So why and how else do we use digesters? One of the biggest pushes for digester use in the industrial space is focused on either biological sludge, DAF sludge, and hauling reduction. So the main commonality between all these industries is they generate some solid, some byproduct, or some sludge of some consistency. And this is probably 80 or 90% of our focus in the market is how do we minimize that sludge volume? How do we reduce that headache? And how do we cut down hauling? And in 90% of the applications, the sludge and the hauling reduction is what drives the ROI on these projects. In some situations, we see plants that have 20, 30, 40, 50 trucks of sludge and byproduct that they're moving on a weekly basis. Those projects tend to have a very favorable ROI. We've seen ROIs on the term of 14 months in some recent cases. So things are changing in the U.S. You know, costs, surcharges, hauling costs tend to escalate. So it's making the digester economics and the digester profile and the ROI a lot easier in these situations. So why and how else are digesters important to industrial operations? Well, they produce on-site renewable energy in the form of biomethane. This can go to RNG, this can go to generators, CHP, so electrical or thermal, and it can go to boilers. So in a lot of cases, when we talk about boiler operation, this is the simplest method of capturing and reusing the biomethane that comes out of the digester process. And in many cases, we see boiler offset up to 25%, right? If an industry is already using natural gas, it's fairly easy to connect to an existing boiler, reduce the natural gas consumption, and have a more holistic, sustainable process there. We're also talking about enhancement of byproducts. So this can be food waste, broken damage, loss, spill, spoil, biological sludges, DAF sludges, where historically these are seen as a cost or a nuisance. When we start talking about anaerobic digestion, when we use these byproducts, use these sources as a form of feedstock for digester, a number of things happen. We're reducing the volumes that have to be moved around the facility or out of the facility. We're creating usable, renewable biomethane day in, day out that can be used for a number of different things. So a lot of good things come from these byproducts. We're also talking about the effluent which comes out of these digesters, the digestate. In most situations, it has great nutrient, great agronomic value. So that's a fancy way of saying it can basically be land applied, much safer way of doing this, of managing the byproducts or managing the effluents that come out of these industries. We're taking out most of the organics, most if not all of the organics out of these sludges. So what's left is primarily the nutrients, so the nitrogen and the phosphorus. And then finally, you know, as we have moved into 2023, 2024, and as we move into 2025, there are tax credits for these digesters if they are applied correctly. Basically, if the biogas or the biomethane from these facilities are repurposed, most industrial sites will qualify for tax credits. 2024, most of our projects are qualifying for 30% tax credit. That's a transferable tax credit. 2025, there is a new, let's say, platform, a new percentage that's being developed. So we're still waiting for the final word on what the tax credits look like for next year. We're not really going to talk about the tax credits much today, but just know that it does impact the current economics of these digester facilities. So the purpose of today is to drive toward why are there different digester technologies? Why does Fluence have multiple technologies? Why are there other technologies on the market? Well, it all comes down to the makeup of the effluent or the makeup of the waste that we're dealing with or that we're focused on. So at a high level, when we look at projects, we tend to break our projects down into three categories. We break the feedstock down into three categories. So why is this important? Well, once we understand which type of feedstock, which type of category we're working with, either carbohydrates, fats, oils, lipids, or proteins, it typically pushes us one direction or another because these constituents have different energy levels and have a different biodegradability time. So if we talk about industries who primarily have carbohydrates, dairy, breweries, distilleries, confectionaries, fruit, vegetables, are prominent industrial effluents and industrial feedstocks that carry high carbohydrates. When we talk about fats, oils, and lipids, again, dairy is kind of a crossover between all these because dairy is it's very versatile. There's a lot of different products. But fats, oils, and lipids, this is going to have the highest energy content. So at a high level, it's kind of like gasoline for your digester facility or digester project. So in a lot of cases, we see industry, the first step they usually take in water and waste management is a dissolved air flotation. So it's purposefully taking out the fats, the oils, the greases, floatables, things like that. Well, if these are not being used as other, let's say, other byproducts or other sources, these constituents are really gasoline for anaerobic digestion. They have such a high energy content. And we'll talk a bit more about that in the next slide. Then we have protein. So again, dairy, meat processing, a lot of particulate matter, different approach just because of the type of byproducts that we're dealing with here and the different energy content that we're dealing with protein. So what does this all mean? Let's try to summarize this, right? So energy contribution and the macronutrients. So in terms of the organic content, the mass of COD per mass of product or byproduct, we can see that the lipids and oils carry the highest, 2.8 kilogram COD value per kilogram of product. So very, very high. We also see that lipids and fats have a relatively low biodegradability time. So again, this kind of drives the equation and drives the type of digester that we're going to use based on the combination of these categories. So when we do our analysis, we're looking for the COD analysis, but also the type of product, right? We want to understand, hey, we're working with more proteins than fats, or we're working with more fats than carbohydrates. So we start to develop a picture of how the bacteria are going to respond, how we need to control the bacteria, and what type of digester process that we need to evaluate here. So let's kind of hone in on one of the key benefits to anaerobic digestion, and that is the methane output. We can talk about pre-treatment all day long. We can talk about the byproduct, the solids, the sludge reduction, but a lot of people want to know what is the expected methane output for different types of feedstock. So again, dealing with standard industry, dairies, confectionaries, rendering facilities, meat facilities, things like that. They're all going to have a different energy content, different organic makeup. But to give you an idea of, let's say, the scalability and the type of output, the type of digester output that we would expect from different industries, this table does a pretty good job of summarizing. So if we look at the primary sludge as an example, on a 1-ton basis, typically primary sludges from your average industry is going to have an equivalent COD value of about 160 gram per liter. So that's quite high, right? So if you're working with dissolved air flotation, this is what we mean by primary sludge. If you're working with a primary clarifier, this is what we mean by primary sludge. So what comes out, what is settled, what is removed from these primary units is typically very high in organic value because there's a lot of particulate matter. Well, on a 1 ton basis, it has the potential of generating over 1,500 cubic feet of methane on a daily basis, just per ton. So we have sites that are moving 10, 20, 30, up to 70, 80 tons a day of primary sludge. So you can start to understand the math and how quickly these digester projects become, very, very sustainable, very holistic, and have a huge impact on the operations and the energy for these facilities. So if we were to break that same primary sludge down into terms of the electrical generation or potential electrical generation, 1 ton can generate roughly 170 kilowatt hours on a daily basis. So here in the US, that's enough to basically power 5 houses. So again, this is very considerable energy content. And as we go down the list, primary sludge is one of the kind of lower energy contents. As we get into facilities that have more fats and oils in their primary makeup, we get into facilities that have rendering facilities as an example. The methane production, the electrical generation really start to skyrocket. So some of these facilities can really be workhorses, and can really go a long way to decreasing the industrial operations by taking this biomethane and taking it back to the factory. They can reduce their own electrical footprint. They can reduce their own natural gas footprint. So there's a lot of different ways to approach this. As we, move into, the 2030, 2050 goals that most companies are setting, obviously carbon offset, carbon footprint is a big focus for a lot of industry. So when we talk about the carbon footprint of some of these, primary sludge, secondary sludges, as they go into these digester facilities, as they create biomethane or as they're applied as electrical energy, there is a CO2 offset associated with this. So if you look at it in terms of how much energy are we reducing, or how much operations are we reducing by negating what we need to pull from the electrical grid, well, we start to see the CO2 offset really has a very important picture. Again, if we look at primary sludge, we're talking about 1 ton per day of primary sludge can reduce the carbon CO2 footprint by 13 tons of CO2 equivalent on an annual basis. So again, when we start talking about facilities that are doing 20, 30, 50, 70 tons, the CO2 offset becomes huge over an annual basis and life cycle analysis. So there's also a lot of drivers for grants and tax offsets and things like that when we talk about carbon footprint. So to summarize quickly, we're about to move into, I think, why most of you are here, the different digester technologies. But just for everyone's benefit, when we apply digester technology, there's a host of different feedstocks that we work with. Primary sludges, excess sludge from wastewater treatment facilities, organic byproducts, fermentation broth, fats, oils, greases, high COD effluents. There's just a number of different areas that we focus in, and this is why we've developed a number of different digester technologies. So let's get right into it. Fluence, on a global basis, we are primarily working with 3 different digester technologies. We have our T-ARC digester facility, we have our ANDAF recuperative thickening digester facility, and then we have our EFC granular high rate digester facility. So let's try to break these down one by one. So the T-ARC facility, this is really a conventional process. It's continuously mixed. Basically what comes in is what goes out. So in this case, your hydraulic retention time and your solids retention time are basically the same, since we do not have any external sludge recirculation or anything to that effect. What goes in is basically what goes out. So these facilities are typically applied to industry effluent or industry byproduct that's high in complex carbs, proteins, and lipids. So typically it's it's a combination of those three. Meat processing is an example where you have a primary effluent, but you also have DAS sludge, but you also have meat byproducts. 9 times out of 10, where we evaluate our what we call our T-ARC for those type of processes. So the T-ARC does a very good job of handling very high COD concentrations above 120 gram per liter, um, as well as a very high percent dry matter. So kind of the natural evolution to the T-ARC was how do we make this process more effective? How do we reduce the hydraulic retention time? So the T-ARC, the continuous stirred process, um, very stable, tried and true. It's probably one of the most applied digester technologies on a global basis, but they tend to be large for the simple reason that, again, what comes in is what goes out. So there's really no control mechanism to control the biota or the biomass in the T-ARC design. So the natural evolution there was, okay, how do we kickstart? How do we increase the biomass, active biomass in the T-ARC? Well, if we look at what's called a recuperative thickening process, we essentially capture a portion of the digestate or a portion of the effluent that comes out of the T-ARC and recirculate a portion of that. We can maintain a higher, let's say, mixed liquor equivalent or a higher solids retention time or a higher active biomass in the reactor. So we can actually have the same amount of biomass in the reactor, but have a smaller reactor volume compared to the traditional T-ARC design. So in this way, we're able to reduce the HRT of the system down to typically 10 to 20 days. We have a few systems operating on an 8-day retention time. I'd say more often than not, we're that 10 to 15-day retention time range. So this becomes a bit more, let's say, favorable for smaller and medium-sized industry. Maybe, they don't have a huge site footprint. So the recuperative thickening process is a way to reduce the system size, let's say. And the way this unit is operated, again, it's highly, let's say, controlled, highly optimized to look for biomass capture and biomass recirculation. And so in a lot of ways, it's actually more stable than the T-ARC process because we can maintain a specific SRT based on the type of feedstock that we have coming in. And I should note here that the HRT, the hydraulic retention time, is different than the solids retention time. Since we're able to capture a portion of the biomass, a portion of that digestate, and recirculate it, we can control the SRT however we want to. So it's a bit independent from the HRT, if you will. So these systems do a very good job with mixed waste. Typically, we limit these to about 100 gram per liter COD load, and the dry matter content up to about 8%. We'll go through that in a bit more detail in the next slides. And the reason for that is the recuperative unit that we have on the backside can typically take solids concentrations up to 8 or 10% at a maximum. So we normally like to work within the 4 to 8% range as kind of the optimized range in these type of facilities. So the third option that we offer is more geared toward your highly soluble effluents. So this is systems like confectionaries or breweries or systems that already have some type of primary treatment or pre-treatment in place. Low solids content, but still has a relatively medium to high COD content. So it's interesting that the evolution of this type of process. So under certain conditions with certain types of feedstock, the bacteria start to behave a bit differently. So when you have more sugars and starches in the feedstock or the effluent coming out of the industrial facility, what you find is the bacteria actually like to grow more in a granular format as opposed to a flock format. So as long as we're able to keep the influence solids below a certain threshold, we can actually start to populate specific size granules, bacteria granules. So what we use is kind of a 3-phase separation inside of the digester, and then we have an external granular separation technology that we use. So we're able to capture certain densities, certain sizes, and recirculate these granules so that we can build up an active biomass within the reactor. Again, very, very stable because we can control the solids retention time in these reactors. So again, it's a bit independent of the hydraulic retention time. We're able to run the biomass concentrations up to 50, 60, 70 grams per liter in some cases. So very, very high active biomass concentration in these types of facilities. So as far as system uses, just to kind of highlight what we just talked about, the T-ARC really geared toward high solids. So this is things like byproduct reduction, hauling reduction, sludge reduction, manure and combined feeds. This is where you more often see the T-ARC, see these type of facilities. So this could be dairy industry, confectionaries with high solids, high waste volume, vegetable processing, fish and meat. The recuperative thickening unit is kind of a combination, something in between here. So typically we see it used for byproduct reduction, but it's also used for pretreatment in a lot of situations for small and medium-sized facilities. This can be used as the primary mechanism to reduce the BODs and the CODs, the organic load, prior to a POTW discharge, if you will. And then on the granular side, this is most common, most applied for pretreatment or primary effluent. So this is geared more towards small and medium-sized facilities. So 100,000 gallons to 1 million gallons a day. We have some facilities that are processing 1 million gallons a day. COD loads around a 4,000 milligram per liter. And ESC does a very good job of, again, it's very high rate. So we're minimizing the footprint, minimizing the area here. Very low hydraulic retention time, but a very high solids retention time. So very stable treatment. More often geared toward dairy processes that already have pretreatment, or breweries that already have the solid separation step, or confectionaries that are dealing with sugars, simple carbohydrates, things of that nature. So let's try to put these in perspective. So we'll give a few configurations for a few different industries to kind of paint a picture of how these different technologies are applied on a holistic spectrum, right? The digester technology, as we mentioned, can be used for byproducts, can be used for primary effluent, can be used for a combination thereof. So let's look at a confectionery facility as kind of a starting point here. So typically what we're going to have is equalization followed by a primary DAF unit. So this is in an effort to really reduce the suspended solids load to our granular process. So again, confectionaries having sugars and starches, the EFC process is typically what we evaluate as step one. So if these confectionaries have a, let's say, a high, spoil or damage product basis, then typically what we look at is separating the two. We would take the soluble effluent to the granular process, very high rate. This is very economic because it allows us to really reduce the digester size, reduce the digester volume. And then we'll take the solids concentrations, both the primary DAF solids and then any byproducts, to a more conventional T-ARC design. Again, both of these units are going to have a biogas output, and depending on the makeup of the solids, depending on the makeup of the effluent, oftentimes we see that both units have the same biogas output. So typically, if we're working with industry, the EFC, the granular process, is applied as a pre-treatment step, if you will. This can go directly to a POTW. In a lot of cases, we can further treat this to a point that it can go to surface water discharge with a few additional steps. So as a second example, we basically take the first confectionery example and we combine the EFC process with the T-ARC process, and we use our recuperative process. So slightly larger unit, but it is simplified in that you're basically taking two steps and combine them into one step. So you can take the primary effluent and you can take the solids, the byproduct, the spoil, the damaged product, and basically put it in the same reactor and have the same combined biogas output, but much more simplified process flow diagram, much more simplified control strategy. So this is something that we use when we have, let's say, a combination of feedstocks, if you will. And again, these units can be used for primary treatment to POTW discharge, or we can add a few additional steps that we can really either eliminate the surcharges, or we can even take it down to surface water discharge in a lot of scenarios. So typical dairy configuration, obviously dairy's very versatile. In most situations, they're dealing with a host of products. It can be different milk varietals, it can be different cheese varietals, sour creams, buttermilks, whipped cream in some cases. So more often than not, we look at our recuperative thickening process simply because we can control the SRT. We can decrease or increase the SRT in this system based on the type of feedstock coming in, based on the type of effluent coming in to these facilities. So very stable, but gives a much higher level of control and autonomy for the dairy industry. So as with most dairies, we have to look at the sulfur and the waste profile to see if a desulfurization process is required. We have to look at discharge requirements. Are we going to POTW? Do we need to eliminate surcharges? Do we need to go to surface water? So a lot of different directions we can go here. Again, when we approach these industries as Fluent's solution mindset that I mentioned up front, we're looking at the whole project, not just the digester. We're looking at what comes into the digester and what comes out of the digester, because more often than not, there are secondary or tertiary steps required to provide a more, let's say, favorable or the best economic picture, specifically when we're talking about surcharges and going to municipalities. And in a lot of areas, as I mentioned, the sludge and the hauling costs drive the situation or drive the equation, but also surcharges in many, many areas drive the equation as well. So when we approach these projects, we look at both. And if we look at a more typical meat processing, this could be meat packing, processor, slaughter. There's a number of different directions, number of different industries here. More often than not, in the meat industry, we're looking at a more conventional T-arc design just because there tends to be a higher percent dry matter, higher percent solids. So a more conventional process is required with an extended HRT. But again, in these cases, the primary driver for these T-arc facilities is the reduction of sludge and the reduction of byproduct, reduction of hauling costs. So just another configuration to consider for a different industry, if you will. So lastly, what I want to leave everyone with is an actual example, an actual project that we've executed. It's a meat processor, 220,000 chicken per day, moving roughly 700 ton per day of byproduct, DAF sludge, all-spec product, and another meat byproduct that comes out of the facility. So on an annual basis, the digester facility and the wastewater facility all together has about a $1.3 million operating cost on an annual basis. But based on capturing the biomethane that comes out of our T-arc process, and T-arc is what we use for this specific facility, we have almost $1 million a year of electrical energy production from this facility, as well as about $150,000 a year of natural gas savings. So the net, the kind of the end outcome, if you will, is the facility actually has more or less eliminated. They're basically in the green. They're in the positive. The energy output far outweighs the annual operating cost for the waste and wastewater facility in this situation. So this is typically true when we get into dairy applications, we get into meat applications. More often than not, the energy that comes out of these facilities is more than enough to pay for the annual operating cost of a complete wastewater facility. As we get into more of the confectionery side or vegetable fruit processing side, more often than not, the surcharge is what drives the equation, just because they tend to have higher flow rates and, let's say, a medium COD concentration, whereas meat processing tends to have more higher solids profile, higher COD content in that solids profile. So That is the 30,000 foot overview. Kind of went through that quickly, but I will open up the floor for any questions and stick around for a few minutes and see what we can answer here.
Yeah, thanks so much, Jason. If you want to just add your questions that you have to the chat section, and we'll get them answered as quickly as we can. Jason, I have a question in the chat already that said, what % of solids do you expect out of the dewatering step for disposal?
Sure. It will depend on the type of digester and the type of dewatering that we use. More often than not, so let's focus on the three digester options, right? So the T-arc design, where it is applied to higher inlet solids or feedstocks with a higher percent solids on the inlet to begin with, it may come out of the system above 8% already. So, screw press, 15, 20% solids is pretty typical. Sometimes we'll even go to a centrifuge, although that's less common. But it's not uncommon to reduce the total solids hauling and the total solids profile by more than 90% in some of these cases.
Great, thank you. I'm not seeing anything else coming through. Does anybody else have any other questions for Jason?
Yeah, I see a question about cover options. So
Yes.
again, yeah, honestly, it tends to be regional. More often than not, we do a double gasomatic cover, membrane type cover for our systems. I would say 90% of what we do is above ground bolted, and depending on the type of feedstock, this could be um, glass lined or stainless bolted above ground. So more often than not, it's going to be a membrane type cover. We do have some solid covers, but again, one driver for the cover is that we as Fluence like to minimize the size of the digesters, right? We air toward, let's say, 1 to 1.5 million gallons. So, 4,000, 5,000 cubic meter digester size versus going to these mega digesters that are, 5, 10 million gallons. And in our situation with smaller digester, number one, it's easier to mix, but number two, the gasomatic membrane type covers is the easiest and most cost effective. All right. You guys are taking it easy on me.
Jason, there's another one in the Q&A that says, what is the smallest flow rate that your digester can handle? Example, 5,000 GPD stream.
Yeah, very good question. So, and very prompt. This is kind of serendipitous. The smallest digester we have ever designed is 26,000 gallons as the digester size, and that was treating between 3,000 gallons a day up to 6,000 gallons a day, but highly, highly concentrated wastewater. So one of the things that we as Fluence have tried to develop is a more economical approach to smaller systems. And in those cases, more often than not, all we're doing is taking the biogas back to a boiler. They're not meant to be these mega biogas production facilities, but they do have the added benefit that you can take it back to a boiler. And again, the operations is pretty much net zero, maybe even positive, because, it's not like we're putting in an aerobic system where we have, all the horsepower for the blowers and things of that nature. So very holistic, very, let's say, energy independent type system for these small systems as well. Yeah, I see a question from Mark about the
Yeah, I see a few more
disposal.
coming in.
Yep. So I see a question from Mark about the disposal mechanisms here and the fees. It's going to depend on the industry and what's in it. A lot of states are driving toward less. Some states are driving toward less land application, and other states are driving toward less landfill application. So it becomes really important to understand the whole picture, because if we're taking out all of the organics and we have a lot of nutrient left, then in most situations it can be land applied, but some states, some regulators, want to profile on what's actually in the solids going on the land. So I
Great. And
see.
then another one. Oh, do you see this other one?
Yep, yeah. Trying to
Okay.
take them one by one here. Yeah, so I see a comment from Greg about applicability for municipal cogen. Yeah, Greg, to be completely honest, we don't really focus on the municipal side much. Typically, if there is a cogen facility like a post-consumer waste or landfill diversion, organic waste diversion, we would run it through one of our partner friends who can manage the project from the top down. We do have the digester technology, but specific to the municipal space, there's kind of two ways to look at it. You have municipalities, and then you have the municipal post-consumer waste. So post-consumer waste, we do kind of dive in. Municipal biosolids, it's not something that we're really interested in, just because in the U.S. market, it tends to be more driven by consultants and contractors more than anything. Very good. Well, if always, if anyone out there needs to reach out, feel free to email, text, call. Be more than happy to continue the conversations and try to answer any questions and keep it going.
Thanks so much, Jason. Thank you, everyone.
All right, I guess we'll call it at that. Sounds good. Thanks, everyone.